Section 6.8 is the counting principle. I can use the counting principle to find probabilities. One way to count the number of possibilities is to use a tree diagram. A tree diagram uses branching to list choices. In example 1, you are buying new eyeglasses and must choose the frame material and shape. The frame material can be plastic or metal. The frame shape can be rectangular, oval, cat's eyes, or round. How many different frames are possible? So when we look here, our frame material options are plastic and metal. And we're going to make branches here kind of like when we made factor trees, but sideways instead of down. So starting with plastic, we can have any of these 4 shapes. We could have rectangular, we could have oval, we could have cat's eye, or we could have round. With metal, we could have the same. We could have rectangular, we could have oval, we could have cat's eye, or we could have round. How many different frames are possible? If we look here, we could have plastic rectangular, plastic oval, plastic cat's eye, plastic round, metal rectangular, metal oval, metal cat's eye, metal round. That gives us 1, 2, 3, 4, 5, 6, 7, 8 options. So how many different frames are possible? 8 frames. Now, go ahead and try this one, please. Suppose each of the different eyeglasses in example 1 also comes in 2 colors, black and red. Copy the tree diagram above and add the new choices. How many new possible choices for frames are there? So I'm just going to continue this up here. We could also have black or red. We could have black or red. We could have plastic cat's eyes that are black or plastic cat's eyes that are red. Plastic rounds that are red or plastic rounds that are black. Rectangular metals that are black, rectangular rounds that are red. Metal, rectangular, red. We could have metal, oval, black, metal, oval, red, metal cat's eyes, red, metal cat's eyes, black, and metal round, red, and metal cat's eyes, black. So our total options here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 total options. And again, we can use that tree diagram to find those and to list them all. So if we want to know what are all the options, tree diagrams are a great way because we can see all of our options. We could have plastic, one second, computer's being slow. Plastic, cat's eyes in red. We could have metal, oval in black. We could have plastic, rectangular in black. We could have any of those options. So if we want to list out all the options, tree diagrams are a great way to do that. But if all we're looking for is the total number of options, then the counting principle here is very helpful. If one event can occur in m number of ways, and for each of those ways a second event can occur in n number of ways, then the number of ways that the 2 events can occur together is m times n. What we mean here, guys, is if there's 2 different types of materials, and there's 4 different types of shapes, we can multiply those numbers together and get that there are 8 different types of glasses. This counting principle can be extended to 3 or more events. So let's say we had 2 frames, materials, and 4 frame shapes, and 2 frame colors. We can multiply all 3 of those together and get 16 options. So again, if we want to list out all of the options because we're wondering what the options are, then a tree diagram is great. But if all we're looking for is the number of options, then this counting principle is going to be a lot faster. In example 2 here, you roll 2 6-sided dice. One is red and one is blue. Use the counting principle to find the number of different outcomes that are possible. So for our red die, the options are 6. We could roll a 1, a 2, a 3, a 4, a 5, or a 6. For our blue die, we have the same. We could roll a 1, a 2, a 3, a 4, a 5, and a 6. So our counting principle tells us that we can take those two values and multiply them together to get our total number of outcomes, which is 36. We could have started off with red 1 and listed all of our options here. We could have said we also could have had a blue 1, blue 2, 3, 4, 5, and 6, like in a tree diagram, and done the same for red 2, and gone that way and listed out all 36 options. But using our counting principle, since all we're looking for are how many outcomes there are, was a lot faster. Checkpoint here. How many different outcomes are possible when you flip a coin and roll a 6-sided die? Go ahead and give this a try. Okay, when we flip a coin, there are 2 options. We can get heads or we can get tails. When we roll a 6-sided die, there are 6 options. We can get a 1, a 2, a 3, a 4, a 5, or a 6. And our counting principle says we can multiply those together. 2 times 6 and get 12 options. Again, if we wanted to, we could have done a tree diagram. We could have gotten heads with a 1, a 2, a 3, a 4, a 5, or a 6. And we could have gotten tails with a 1, a 2, a 3, a 4, a 5, and a 6. And then counted up our 12 options there as well. But our counting principle was faster. In example 3 here, a combination lock has 40 numbers on its dial. To open the lock, you must turn the dial right to the first number, left to the second number, then right to the third number. You randomly choose 3 numbers on the lock. What is the probability that you choose the correct combination? Remember that probability is the number of things that we want or successes or favorable outcomes compared to all of the possibilities. So in this particular problem, we're looking for the correct combinations. And when we're talking about a lock, specifically a combination lock, guys, there's only one possible combination. So the number of wants or successes or yeses is just 1. Now we need to figure out what all the possibilities are. And we know that there's 3 numbers on this lock. There's 40 numbers on the dial. So for the first number, there's 40 possibilities. For the second number, there's 40 possibilities. And for the third number, there's again 40 possibilities. So we can use our counting principle, and that tells us we're going to multiply those together. And we'll get 16,000. So the total number of possibilities with a 40 number combination lock is 16,000. So the probability that you would choose the right combination on your first guess, considering that it's completely random, it's not like somebody's birthday or something like that, is 1 out of 16,000. That doesn't mean that you couldn't guess it right the first time on accident, but your probability of doing that is 1 in 16,000, which means if you tried it 16,000 times, you would guess it right the first time once. And that's a theoretical probability. Remember that experimental probability could be a little bit different than that. Another way to think about this, guys, is if we had a 10 number lock, we'd have 10 for the first number and 10 for the second and 10 for the third, so 1,000 options. And that makes a little bit more sense when we think about listing them all off. We could have 0, 0, 0, 0, 0, 1, 0, 0, 2, all the way until we had 999. So we could see all 1,000 options here a little bit easier than we could with 40, 40, 40, but we still don't want to list them all out. So we could do the same thing by listing out all of our possibilities here with a tree diagram, but it's going to take us a long time to get to 1,000 or to get to 16,000. So using that counting principle is definitely beneficial. And that's all I have for you for section 6.8.